So, when we talk about integration, this is what you cover about the third chapter, or third or fourth chapter of your calculus course. Because we're going to skip in a bunch of the other, remember there's lots of derivative rules that we're not covering, so we're going to do just a couple of the basic integration rules. Now, the general goal of integration, what's the general goal of derivatives? Find the slope of a line anywhere, or any line, the slope of the tangent line. Now, when we talk about integration, the overall goal was how do we find the area of a shape? So, how would you find the area of this shape? Formula. Length times width, so x times y. Now, how about this one? Do you have any formulas for dealing with that?
Yes.
What is it?
I believe, but I don't know.
Okay.
Okay.
Yeah. So this is where it gets much more complicated from dealing
that
with
a
areas.
circle?
No.
It's a half circle.
It's not even in any shape. And we could write an equation that describes it. But anyway, this is the general idea. As soon as you don't have a nice shape, getting area gets much more challenging. In fact, as soon as you start putting curves and stuff like this, you have to use calculus to get it.
What exactly is curves?
Okay? It's an extension of algebra and dealing with curves and things that change.
Is there more graphs in calculus?
Is there more graph? What do you mean?
Graphs
More than what?
than algebra.
Generally less. It's more of it's a lot more theory than application. All of those lots of applications. Like when we talk about derivatives using the instantaneous velocity, that's one of the applications of calculus. Now, the definition of your definite integral. So it's going to get rid of that. Our definition. That's what this symbol means, is the integral from a to b of f of x dx. So this tells us the starting point. So when you're looking at the graph, we're going from some point A, if we're just doing something like this, to some point B over here. And our goal is finding what's the area under this curve.
But it doesn't touch the,
But it's the area within this range. From A to B. So A tells us our starting point. B tells us where we're ending. F of x is the graph of this function right here. Or the equation of the function. Dx tells us what variable we're using. This is important because if you go and take calculus, you're going to deal with double and triple integrals where you're going to have to deal with several different variables in the same problem, in the same calculus.
Wait, what's the
Dx says what is our variable we're working with.
What variable?
So this says we're working with x in
Is it
general.
in the parentheses?
Well, f of x says it's a function of x. Dx says we're doing the derivative or integral with respect to x.
So what would it be like if it weren't x?
Okay, so we could do something like this: integral of f of x, say from 2 to 4 of f of x to dy. This is doable.
Why?
I just chose a different variable. So this says we would be doing the integral with respect to y as opposed to with respect to x. The function of x, but I'm doing the integral with y. Or dn, it doesn't matter. I'm just saying you could do it in this way.
And then that's to multiple different things?
Yes.
Would the
That's
answer change?
Yes.
Why would it change?
Because if you're using a different variable, then you're doing the integral differently. So patience. I think it'll probably make a bit more sense. Don't worry about that. Okay. Now the definition of this is equal to the limit as n goes to infinity of the sum as I goes from 1 to n of f of xi delta x, where delta x, yes, delta x is equal to b minus a over n, and xi is equal to a plus I delta x. Now, this is our overall definition. Now I'm going to explain why we can justify this.
And you can memorize that in calculus?
What is the
Yeah.
I?
Do you have to
What is
memorize
I?
it here?
Yeah, what is the I?
I is the variable in the sum.
Oh.
Do you have to memorize it here?
I don't think I'm going to say that.
Nice. You're nice.
However, you'll need to know how to do the whole operation. But first, we want to justify what this is doing. Okay? So, delta x, what does delta mean?
Change.
Change in. So we are taking some function value times the change in x. So consider if we had a graph here. I'm just going to do let's just do something like this. What is a shape we do, and we want the area of that. What is a shape we know how to calculate the area of?
Circle.
Okay? So we could, if we wanted, start putting circles in here. Okay. Okay. So we could do circles. But then, so each thing here, and then we're going to have, now each one of these things we're going to have to put little circles and littler circles and so on.
Circle not a good option.
Okay. But we could theoretically do it with circles. Now, it would get much, much more complicated. We're not going to use circles, though.
Rectangle.
Okay. So typically, rectangles is
Trapezoid.
Okay? There is later, we're going to look at rectangles today. Later, if you take calculus, you'll learn that there's a trapezoid way that's actually a bit more efficient than the rectangular way.
It's a trapezoid.
Can you
So-
put this with trapezoid way?
It's more work, I'll put it that way. So, we're going
But
to
it's
do,
easier.
so, we're going to do, let's say this is from 0 to 10 for now. And let's divide this into 10 rectangles. Probably shouldn't have done 10, but that's it. 1, 2,
It's not a rectangle.
patience. Okay. They should be all equally spaced, so let's try that a bit better. I'm trying to do about there, there. So 1, 2, 3.
Wait, so A is the starting point?
Yeah, and B is your ending point. So I'm trying to get these equal width.
Yeah, we get the idea.
Not doing very well at that, but
We'll get the idea.
It's okay.
this is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now we're going to just make it a rectangle just like this. So each one of these, in this case it's fairly flat, up a little bit. Now, is this going to be more or less than the area?
More. Just kidding, hold up.
That would be, I don't know, it would be somewhere in the right neighborhood, right?
Yeah.
And here we've got a bit, we're counting a little bit extra here, but here we're not counting a section there, so, but it's going to give us into the right neighborhood.
Mm-hmm. How do you know how short 7, 8, and 9?
Well, what I was doing with this one is a right-handed rectangle. Let's see, was that the right term? What do you mean? Yeah, we're just using the right endpoint. So we're just taking from 1 going up until we hit the graph. So this right here would be f of 1. This would be f of 2. Now, what's the width of each one of these rectangles? 1. So this is 1, this is 1, this is 1, and so on.
Mm-hmm.
So, to get the area of this, we would have to say, what is the height? So, if we said this was the green is f of x, what would the height of this first one be? F of 1. So we'd have 1 times f of 1 for the area of that first rectangle.
Why do you,
Length, or width times height,
How do you know the
what's the
height?
height?
f of 1. Well, whatever we get if we plug in 1
To what?
to the function. I didn't tell you what the function is, but we're plugging 1 in.
You would get the same function.
Well, we get 1 times whatever we get when we plug in 1.
Oh,
It'd be constant though. Like, for example, if this is an x squared graph, it would be 1 squared. You follow that? Sort of? Okay, how do we get the area of the second one? Okay, what's the width of the second triangle? 1, what's the height? F of 2. So we've got the width of 1 right here, and the height, F of 2.
why are you multiplying it by 1?
What's the area? How do you get the area?
Oh, the function gives you the height?
Yeah.
Oh,
So we got our length here, our width, and our height. Or length and width, however you want to do it. And then we can use the next one by saying 1 times f of 3. And so on. And we could add all these together. We would get a reasonable approximation of the area. What could we do to get a better approximation?
The more rectangles you use, the better.
Okay. So using more rectangles gives us better data, right?
More working.
Yeah, to a point.
Isn't
But
that
let's say if we
how
did, instead of 10 rectangles, we did 20. We'd get more accurate results, right? Well, if we did 40. What if we did 1,000? What if we did 1,000,000? Where's it going? Infinite. If we did an infinite number of rectangles, we would be exact on. Right? So, this is why we're saying we're going to let n, which is the number of rectangles, go to infinity. Okay? So at the end, that's why we're saying we're taking the limit as our number of rectangles goes to infinity. This one says we're adding up the first rectangle, the second rectangle, until we get to an infinite number. Remember, we're saying we're doing an infinite number of rectangles. That's where this is coming from. Does this f of xi look familiar?
No.
Is that times I or subscript?
Subscript I.
Oh, well,
We did f of each one of these, right? So what we're doing is this right here represents the height of the function.
sorry.
So we're plugging in
Oh,
the first x, the second x, the third x,
F of
f of x1, f of x2, f of x3, f of x4. So we're plugging in all the different x's going along.
So you're only plugging F of 1, what's the F?
Are you looking at this one here?
Yeah.
So let's consider more general. Instead of having numbers here, this would be x1, this would be x2, x3, all the way until we get to x10 in this case. And we would plug in, this would be f of x1, f of x2, and so on, right? So we're doing it more generally and saying we're going to let the number of x's, the i's are going from 1 until we get to an infinite number of them. That's what we're saying. And we're just plugging in all the x's. Okay? So is everybody with me on that? So that's where this part is coming from. This is telling us the height of each rectangle. Now, what do we need to get the other part? The width. How the change in x, which is taking our endpoint minus the beginning point divided by the number of rectangles. So if, looking at this one, if we had 10, we went from 0 to 10, and we divided it into 10 rectangles. We'd do 10 minus 0 over 10 to tell us what is the width of each rectangle. So if we had 20 rectangles, it would be 10 minus 0 divided by 20, and each rectangle would be how wide? 1/2. So right here, in general, we're saying we're let it going, the end of it minus the beginning to tell us how wide it is, and divided by how many rectangles we're doing. And that should tell us the width of each rectangle.
What about the equation for...
This right here?
Yeah.
Okay. So consider if you're starting at A. Okay? If we want the first x, Okay? So we want x1, we would start at A. So let's just say A was 0, like in this case down here, plus, which one are we looking for? 1,
One.
because if we're looking for x1,
Oh, right.
times, what's the width of it?
1.
1. So f of the first one is going to be at 1, because 0 plus 1 times 1. If we wanted x2, we start at 0 plus 2 this time, times 1. And we would get 2.
Is A0?
X3, well, yeah,
A is the third number, yeah, I got it.
and for this case, I'm looking at this case right here. So what I'm doing is trying to locate where this point right here is, using this function. So here we were adding 1 width, here now we're adding 2 widths, 3 widths, and so on. So, is anybody confused on that one?
What would it look like if you did
A natural problem?
yeah.
Okay, yeah, we're going to get to that. But this is the structure we're working with. I want to make sure you understand why, the justification why this gives us the area of the thing. So overall we're doing, we're breaking it an infinite number of parts. We're adding up the area of each one of these parts. That's what this part does. This says the height of our part times the width of the part. Okay, so now, let's first do one that everybody knows that we can easily calculate the area using our old method. So let's just do, what is the area of, let's say, f of x equals, say, negative 2x plus 6 from 0 to 3. So we're going to do this first using our pre-calculus or before we take calculus method. So let's say 1, 2, 3. What's the graph of this going to be?
A line.
Okay, it's going to be a line. What's the y-intercept? 6. What's the x-intercept? 3. So the goal is, we want the area of this. How would you get it using pre-calculus method?
That's a big.
3 times x2.
Yeah, length times width divided by 2. Right? So we have 3, 6, 3 times 6 is 18, so our area equals 9. Okay, so now we're going to use our calculus method of doing this. The same problem, but everybody saw this is y is 9, right? Okay, so our formula, we say the limit as n goes to infinity of the sum as I equals 1 to n of, now we have to, what is f of xi? Or what is xi first? And what is delta x? Delta x might be what we want to do first.
Delta x is 1. No. What?
What is delta x equal to?
B minus A over N.
Yeah, right here. Delta x, b minus a over n. So 3 minus 0 over n.
I think
3n.
What?
Oh, how do we know what N is?
Well, we don't know what n is. We need, remember, we're going to be plugging that in and letting n go to infinity.
What is N?
N is the number of boxes we're dividing it into.
Oh, so that doesn't.
We're not plugging a number in for it
Oh.
until we evaluate the limit here. Okay? Now, what is xi going to be?
Xi is gonna be 3n.
Okay? We start with 0 plus I delta x. So 0 plus I, and what is delta x? 3 over n.
Is I,
So we get 3I over n,
wait, is that I is a variable I, right? Or do you
Yes.
imagine?
the variable I. Okay, so we've got delta x, or we've got xi, and we've got delta x.
Will I always be variable?
Yes. Unless you're actually dealing with and measuring things, which then you have to be dealing with something very different. So don't worry about it.
So it'll never be a constant?
two different letters.
Well, you're not going to use the imaginary number. You're not going to use the imaginary number when we're dealing with this. Possibly if you take some calculus, you might run into it, but not for right now.
Are we ever going to look for what I is?
No. Remember, we're letting I go from 1 to n. Remember-
For n?
Well, n is going to go to infinity. Okay, so the next thing we need to do is we need to get f of xi. Which means what we need to plug xi, which we've calculated, into x. So what are we going to get?
6 I n.
Negative 2,
That's negative
3I over n, plus 6.
which is negative 6.
Okay, so everybody see where that came from? Okay, and then the next step is we multiply by delta x. So we're going to multiply it by 3 over n. Okay, so everybody with me? So let's simplify this a little bit. We know it's going to be the limit as n goes to infinity of the sum I equals 1 to n of, is it going to be a negative 6I over n plus 6 times 3 over n. Now, this is where once we get to this point, this is where we start having to get the more complicated part. Now, is this part here going to be affected as I changes?
No.
Yeah.
No.
Oh,
This part right here, as I changes,
Okay, no.
not going to be affected. So we can take that out of the sum. So we can rewrite this as the limit n goes to infinity of 3 over n, and the sum is I equals 1 to n. And now I'm going to separate this into two parts. As negative 6I over n plus the sum I equals 1 to n of 6.
That's always been 6.
Well, in this case, yes.
No, on the right, no, right.
Yes. Well, in this case, in this problem. Okay, is anybody confused where that came from? Okay? All we did is took this sum and applied it and took the sum, and because one of our sum rules, we can take everything in here and do each one individually. Now let's see, continuing on, the limit n goes to infinity of 3 over n times. Now, looking at this part, is there anything we can take out of it? No, both the negative 6 and the n. Notice, those aren't affected by I, so I'm going to rewrite it as negative 6 over n of the sum I equals 1 to n of I. Makes it very easy, right?
Why was it necessary?
It'll make everything, the computations easier. It's not strictly necessary. Okay? Plus, next one, sum I equals 1 to n. I'm going to pull the 6 out and leave 1 in.
You can do that?
Yeah? Now,
What if the I had been on the bottom?
is this I been on the bottom?
Yeah, what if you went over it?
Yes. Okay, now we're going to go back. Do you remember 10.4?
Stop.
Now, you're not going to be doing proofs like that, but we're going to use some of our rules we learned from there. What is this? The sum of I equals 1 to n of I equal to? No.
No.
1.
So n to infinity of 3 over n, okay, and then we're going to have a negative 6 over n. So for example, we're doing 1 plus 2 plus 3 plus 4 plus 5 all the way to infinity, or all the way to n. Okay, it's going to be, does this look familiar?
Does it look like
N over 2
Oh.
times
A1. No? Am I in the wrong one?
1 plus n.
AN.
What's between a negative 6 over n and
Multiplication. Since this is multiplying out here, and if you want to hint, look at the bottom of page
So is it supposedly,
page 777. It's got the rules for a constant. It's got the rule for I squared, and so on.
wait, hold on,
what
I got it.
is this?
777. Yeah, the bottom 777, and you'll notice this rule is there. I'm going to rewrite it to make it as up here 1 plus n. Doesn't matter how I write it. But that, if you look at the formula there, this part right here becomes that. Yes.
Isn't n the thing that we did, isn't it 1 plus 2 plus 3 to the infinity, right?
Yes.
Isn't it supposedly negative 1 over 12?
Yes.
So we can do that?
No.
Why not?
Because we're going to be using we have to let n go to infinity. We haven't let n go to infinity yet. Right now we're just doing the sum. Right? N has not gone to infinity.
But if n does, then it's
Yeah.
negative 1/2, 1/12.
Negative 112. But we have to deal with this first. Yeah, you can't let n go to infinity until we've start dealing with all the rest.
Why is it negative 1/12? I still don't understand.
Okay, so ignore it for now.
Okay.
We're working on this. Now, what's the sum? What's the second one going to equal?
One and 6?
Okay. 6n.
Oh, yeah.
Okay? Because we're adding up 1 n times. So we have 1 plus 1 plus 1 plus 1 plus 1. That's what this says, n times. And then we're multiplying by 6.
1 plus 1 will always be infinity.
But we're not going to infinity, we're going to n.
Oh.
Okay? So everybody with me on that? We're good. Now we're going to simplify this. But this is, I'm going to give you a shortcut here. We are going to be letting n go to infinity. Eventually. Actually, let's combine like terms, or not combine, but get these into the same fraction. So we're going to do the limit n goes to infinity of 3 over n. On top we're going to have a negative 6 n, negative 6 n, n plus 1. And what would I need for this one? So we have to combine it with these. Yeah, I got to multiply with 2n, so plus 12n squared, all over 2n. Just down here.
Why 2 squared?
Well, you got to get a common denominator and multiply by times 2n over 2n. And let's do another step for simplifying. N equals to infinity of 3 over n, and negative, we're going to have a negative 6n times n gives us a negative 6n squared, plus 12n squared gives us 6n squared, and then minus 6n over 2n.
What?
Okay, negative 6n times n gives us a negative 6n squared, plus 12n squared is 6n squared, and then negative 6n times 1 is a negative 6n. And the limit n goes to infinity of,
Wait, quick question.
yeah, cancel?
Yeah, take out 2 and 10. What is that?
So, which leaves what 2n here minus
3.
3n minus 3. So we have 3, and let's just make it 9n minus 9 over n.
What?
I just multiply this part out here.
How can 3 over n just come out like that? I just don't understand.
Because,
Up
no,
there,
does, up here, does this, all the way up. Does this 3 over n get a change as I change it? So if I plug it, so if, for example, if this equals 1, I'd have 1 times 3 over n. And then plug in the next one, I'd have plus something else times 3 over n, plus something else times 3 over n, plus something else times 3 over n, right? So might as well factor 3 over n out before we do all the additions. Meaning, so if I had, say, 4x squared plus 5x, I can factor it out before doing the addition. So I could write this as x times 4x plus 5, and I could do this addition and then multiply by x. That's the general idea of what's going on. Okay, now what's going to happen is n goes to infinity.
Infinity.
What happens if it's plus n
Okay,
squared?
I did negative 6n, so I did this and make it negative 6n squared
Oh,
minus 6n and then combine it with 12 and
n goes to infinity, it's gonna go to 9.
This equals 9. And let's see. Oh, we got area equals 9 already.
That's
What?
such a long run that way.
Why would we have to do it that way?
Get it. Oh, this was a nice function.
Yeah.
Just change, like, how about we could change things like curves?
Okay, so we're going to do a curve too.
No, we don't have to do a curve.
One problem.
We
Okay,
can wait until we go to custom.
no, we can't.
so let's see. Let's do this on y equals x squared from 0 to 4. Remember, this graph is going to look something like this. And we want the area of this, as this is 0 to 4. All of this, right? That's what we want.
What did you just draw?
So, integral from 0 to 4 of x squared dx.
Well, I don't know what you just draw.
Okay, then look more details. So first, what's xi equal to?
Oh, okay.
Why does it use x? Is it because you're finding 0 to 4?
Well, because x is the one that's changing. We're plugging in different values of x. Remember, you're doing,
Why did we say that earlier?
because I said we're going with respect to x.
That's just a big word.
Okay. What's xi equal to?
xi equals to...
Actually, delta x. Get delta x first.
Delta x is equal to
4 over n.
4 over n. Therefore, xi is equal to
4 over n. I.
4i over n. Okay, so everybody with me on that? So now we're doing the limit as n goes to infinity of the sum I equals 1 to n of 4i over n squared times 4 over n.
F is 4i over n.
Yep, so I plug 4i over n
Why should
into here. So I plugged it into my function.
Oh, right.
So as n goes to infinity, this is going to be the sum I equals 1 to n of 16i squared over n squared times 4 over n. Now what am I going to be able to take out of this? I can multiply 4 times 16.
Yeah. You can take most of it out.
Okay, so I'm going to get the limit as n goes to infinity of
64 over n to the third.
64 over n cubed, and what's left over?
I squared.
So I equals 1 to n of I squared. Right?
What is that?
N cubed?
So I did n times n, I get n cubed on the bottom.
Where does this before go?
4 times 16?
Yeah. Or did you just combine?
Yeah, I just combined this stuff.
So 64 over n cubed.
It's 64 over n cubed. Now, according to our rule, what's I the sum of I equals 1 to n of I squared equal to?
I don't know.
Is it I squared equals to 1
Is n goes to infinity of 64 over n cubed times I squared is, according to the thing on page 777,
Do we have to memorize that?
n plus 1, no, 2n plus 1, all over 6.
Are we supposed to be able to, like, know it without looking at, like, are we supposed to be able to
No,
come up with it?
I-
Or those are, like, rules?
those are rules.
Do you have to know any calculus?
Possibly,
Memorize it?
possibly, but probably not.
Any AP calculus?
Probably. Okay, now, this looks a bit more complicated, but let's consider, which power of n do we worry about in this?
N cubed.
Okay?
What?
No,
What am I saying?
no, everybody ignored this 9, why?
Oh, because it's not equal.
Yeah, power's the same, we only looked about this part right here, right?
Oh,
So now, looking at this problem right here,
We're like almost done with it.
yeah, we can do this in basic 2 steps now.
We only care about.
Guys, do we care about this n times 1?
No.
No, because it's a lower power than n times n. So, I'm going to put approximate, n goes to infinity, 64 over n cubed, and what's going to be on top that we care about? 2n cubed
Over 6.
over 6. Okay, we don't really care about this 1 because it's going to be a lower power of n. We don't care about this 1. We don't care what happens when 2n times 1 because it's a lower power of n. And when n goes to infinity, we don't care. So what happens? 1 over 3, we get 64 over 3.
Which is?
64 thirds.
In decimal it is?
You can't simplify it.
Yes, you can.
21.3 repeating.
Yeah.
So if you know little tricks like that, this type of problem simplifies a lot goes a lot faster than you might think.
So I can do steps like that?
Yep.
You're showing us the easy problems, aren't you?
Well, this wasn't one of the easier, yeah.
Then so can we do something like?
Let's see, more complicated.
Right.
Problem, we don't have time.
Integral from 0 to 3 of 8 minus 0.6 x squared dx. The ones that have addition and subtraction always seem to take a bit longer. I just said 0 to 3, let's do 1 to 3, just to make it a little different from the 1. Okay, so first, what is delta x?
2n. 2 over n. Just 2 over 3.
No, it's over
I don't
there.
know. Okay, 2 over n.
Why are you yelling at me?
Okay, what is xi? Okay, it's going to be 1 plus,
2 I over n.
Oh, okay.
1 plus 2.
okay, do you see why it's 1 plus? Okay. Now, the reason this gets a bit more complicated when we don't start at 0, because now we're going to have to square this. So we're doing the limit as n goes to infinity of the sum I equals 1 to n of 8 minus 0.6 times 1 plus 2i over n squared times 2 over n.
What's just happened? Why did you put that? Oh. I got it.
So the limit of n goes to infinity of, I'm just going to pull the 2 over n out right now, so I don't have to get
Can you not put the limit of n of infinity into the end? Like,
we
you know
have
what I mean?
8 minus 0.6 times, let's see, 1 plus, let's see, 2i over n times 1, so plus 4i over n plus 4i squared over n squared. FOIL. 2i over n times 1, 1 times 2i over n gives us 2i over n plus 2i over n, which is 4i over n,
Right.
and then squared. So, the limit n goes to infinity of 2 over n And I'm going to start breaking this up to make it a, actually, 0.6 times 1 is
0.6.
0.6. Negative 0.6 minus 2.4, I think. Come on. 2.4i over n.
Is this what the side
Minus-
parentheses?
Yeah. Well, I'm distributing this 0.6. 2.4i squared over n squared. Am I correct there?
Yeah.
Okay. 8 minus 0.6 is,
Don't you have to square 2.4?
7.4.
no, because I squared it already here. I made it 4i squared. So I already squared, it's just the I being squared here, not the,
Oh, okay.
okay, so 8 minus 0.6,
7.4.
7.4, okay, that's the first part. That's just the constant. Then minus sum I equals 1 to n of 2.4, I'm going to pull that out, 2.4 over n of I minus 2.4 over n squared of sum I equals 1 to n of I squared.
Minus 2.4.
Why didn't you take the other one out?
Why did you take 2.4 over and split it out?
Where? Right here?
Yeah.
I pulled it out of this sum.
Why didn't you put it in the one to the left?
Over here?
Yeah.
Because-
No, in.
In here?
Yeah.
Because no, this doesn't have an n squared. This one is just based on this part became here. This one right here became this part. So basically I just took each one of these parts. So the first part was this combined with that, and it became this part. Second one I did just this negative 2.4i over n became this.
Should you pull 7.4 out? Just right there.
Oh, it doesn't matter, it doesn't matter.
Okay.
This is 7.4, becomes 7.4n.
Yeah, it's just going to become 10.4 n, so it doesn't matter if where I do it. So I'm going to have limit n goes to infinity of 2 over n. This is going to become 7.4 n. Okay? The next one, the I rules are going to have minus 2.4 over n times, let's see, n plus 1 over 2. That's just using our rule from the book. Minus 2.4 over n squared. Again, just using the rule. It is n plus 1, 2n plus 1 over 6, I believe.
Yeah.
Okay? So now I'm going to apply this to each part. 2 times 7.4, 14.8. N goes to infinity. The n's going to cancel. Here, I say the n cancels there. Then I'm going to have minus 2.4 n,
You can cancel.
okay, over n. Because of the n here.
And where?
Yeah, that's it. Well, we have 2 times 2.4, so let's just do 4.8 n squared over n squared. That way, I'm doing n times n to get n squared on top.
But I thought you canceled that in.
Well, I tried to undo that, just so you don't see too much cancellation. And then just the n here. Don't worry about if it would just make this n over n if you want.
Shouldn't it be 4.8 just to cancel it?
Yeah.
Yeah, that makes sense.
Where does the plus 1 go?
Yeah, because remember, is that going to affect it if n goes to infinity?
Oh, no, so I like the square better.
Okay, n squared. It's not affecting our problem at all, right? Because that's going to cancel it away.
Shouldn't we not have 14.8?
Minus. Oh, we need a 2 here as well because of the 2 there.
Yeah.
Okay, and then we're going to have a 4.8 times. We're going to have 2n cubed over 6n cubed.
Why is 2.4 equal 20?
Times 2 from this 2?
Not the 2n?
Yeah, and then I left that 2 in here.
You have to apply the 2n, 2
But-
over n to the left to everything?
Well, this has to apply to here, has to apply here, and has to apply here. That's where all the 4.8 and 4.8 came from. And this one, at this point, the n cubes are going to go away.
And
So you're going to have 4.8 minus 2.4 minus the 9.6 over 6.
One,
What
no,
about?
no. 1.6.
So 1.6, yeah.
Anyway, this is what you get.
N go?
Because we're letting n go to this, all the n squared and n squared, n cubed and n cubed.
Please don't go to the numbers, I don't think people understand it. Yeah.